Hi there, this is Tommy Woods, and this is another video to try and explain a little bit more about the system that I'm investigating and some of the results that suggest that there might be some Lorentz covariance of this system, or at least satisfaction of Einstein's relativity postulate that the speed of light in all inertial reference frames is constant. So in my last video, I ended up basically doing many runs of the system, what I call microstate runs, where it's just showing one instance of what a possible series of states could be following the given update rules. And I run a bunch of these. And then for each one of these, I use the output state as an input state for another series of runs. Now, along each one of these series of runs, I enforce the system to be in an inertial frame. And what happens in the inertial frame is it takes a little bit of time for the centralized point particle to become aware that the system is in this inertial frame. So it's sort of, if you imagine averaging over all of these loops, it's going to be, or all of these microstate paths, it's going to be a sort of gradual process, or it'll be sort of a gradual thing that the overall macro state evolution of the system, or the sort of the ensemble of these microstate paths, the sort of the mean behavior of the system, the average behavior of the system, it will appear to be sort of gradually moving into an inertial frame. And so what I did with the last video was I showed some of the results that I got with regards to the distributions of some of these velocities, or the effective velocities. I went into some detail about how I calculated those velocities. It's to do with measuring the speed at which light travels between 2 points in space in the system, and the point at which the centralized observer observes those moments where the light leaves one of the points, and also when the light reaches the second point, and measuring those points in space-time, and that gives you a velocity. And so what you're looking at here is each one of these numbers is basically the mean of one microstate path, and then it's allowed to, so if you see, we've done this 500 time steps is the length of the microstate path. So here that will correspond to T0 to T1. And then what we've done is we've taken the initial inertial frame period to be the first 25 seconds of 1,000, first 25 seconds, and actually what we've got here is T2, which is about 100. And each one of these is the average of 100 loops from there. So we're basically averaging these values here, and this is at time 25. So as you see, we've got all these different values. Each one of these values is essentially one inertial frame. So you would actually want to see these values at some limit all tend towards values that are very close to 1. Because at the moment what it looks like, you've got some values that are like 3, some values that are 1. And what I showed in the last video was that when you take all of the values of the velocities and you work out, okay, well, what is the distribution of those values? So it basically, each one of these, there's 100 values in each of these, making the mean for each one of these inertial frames. And we're just decomposing it. So here, let's say there's 1, 2, 3, like there's, I don't know how many are there, 25 runs. So it's like 25 here. So it'd be 25 times 100, which is, 2,500 different runs that each has their own velocity. And when you take that distribution and you plot it as a box plot, you get this value, right? You get this distribution. And you can see, obviously, it's not quite landing on 1, but given the range of this data, it's very skewed to being around 1. And this is what I'm seeing in all of the data, that the median, the middle value of all of these velocities is sort of stuck around 1. And this is sort of intuitive, because from the perspective of the if you imagine that the graph is a measure of distance, and the distance is essentially the amount of space elements between 2-point particles. That makes perfect sense in the context of the metric of the graph, right? But when you're embedding it into a space, that's not necessarily immediately true that it would be traveling at this speed, right? Because that's the speed that's traveling at in the graph. But in the embedded space, what we're seeing is as you average it, you sort of take a mean or an average value of these velocities over all of the inertial reference frames. It comes to around about 1. But you still have this deviation, right, from 1 in these individual inertial reference frames. So that's where I'm moving the next part of the investigation. So I think one thing that's important to add before moving on is that this distribution is essentially all of the velocities, the distribution of all the velocities combined of the different inertial frames of the different the inertial frames are basically created by a single microstate path that then we allow to evolve, use as an input to evolve a ensemble of other microstate paths. Along that microstate path, we then fix it in an inertial frame, and some point along there, the state becomes aware that the system is in an inertial frame and then will behave in that way. And so what we're seeing here is we're essentially seeing that these velocities, these average velocities that we're seeing, are sort of skewed to be around 1. And so what the effect of that is that when we look at the mean value, obviously the mean value is going to be quite largely affected by the larger values here, but there's a definite skewing to be below 1 or around 1. And so when you sort of balance the mean with the median, it feels a little bit like 1 is the value of 1 is holding it there, even in the embedded space. This is interesting because in the context of the graph, when we think about the graph, it's it has its own metric essentially, and the own metric is given by the effective microstate, the effective edge weights, or at least another way of saying it is the number of space elements on a given interaction edge that the centralized point particle is aware of, right? And the centralized point particle is the point particle that is at the origin, and it represents the observer of the system. And so there is a sort of two metrics going on in a way. There's the metric of the state graph, and that corresponds to the lengths on the state graph that the centralized point particle is aware of. But then there's also the lengths in real space. That's in the embedding, right? So in the case of the actual graph, it makes perfect sense that the speed of light is constant in all the reference frames, because it's just the information is propagating at one space element per time step, irrelevant of what's going on in the embedded space. But what's interesting here is that we're seeing, even in the embedded space, that the values of the velocities are highly skewed to be stuck to around 1. Now again, we aren't using a large number of loops yet, and also this is not for individual inertial reference frames, right? Is it? This is overall, right? This is overall it behaves like this. One thing I will say is that the velocities, or the distributions of the velocities, seem to be invariant over the scale of the system as well. And that's where I'm shown. If I go sort of to lower values, you can see this behavior. Lower values are able to do more loops of the system. So here's an example where we're looking at the average wavefront speed and the distribution of that. And here what we're doing with these velocities, these investigations, we're doing a large number of runs, and we're changing the loops, and we're looking at the distribution of the runs. So like I said before, we weren't really looking at the individual inertial reference frames. But now what we would imagine to happen is that these inertial reference frames, their value or their mean, especially for low values here, we're looking at 3 time steps instead of 500, means we're able to do many more loops of the system and investigate the system in more detail. However, there is likely to be some overlap of the microstates that we observe, possibly, depending on how many time steps we go. If we go for smaller number of time steps, it's greater probability of there being a repeat. If we have a large number of time steps and less loops, then there's going to be a lower probability of repeats. And I think that repeats will have some effect on the system. Basically, at the limit of lots and lots of loops, there's a sort of repeating effect due to the Monte Carlo randomness of the Monte Carlo simulation. But then at really small loops, you're not really getting a very good, the noisiness of the system takes over. So in this particular investigation, we are now looking at smaller number of time steps, and we're looking at the distribution of the inertial speeds of the average speeds of the inertial reference frames. And what we're seeing is that as we increase the number of loops, right now that's not the number of runs, that's the number of loops on each inertial reference frames. Okay, so if I go back to my diagram here, that's the number of loops here. As we increase the number of loops, at least for small time steps, what we're seeing is that the standard deviation, that is the amount of spread of this distribution, is decreasing. Now you have to increase the loops by quite a large amount. So for example here, I did this here. This is a sort of first primary example. And we go down here and we get, oh no, it was here, wasn't it? Okay, so this is the first one. So what we're doing here in this investigation is we're doing a number. So we're doing first. Oh, this is the first time step. 1 time step, 2 time steps, 3 time steps. Okay, so that's a little bit different. But okay, yeah. So what we're doing here is we're looking at how changing the number of loops. So in this case, we're changing the loops, and the loops are going up by factors of powers of 2, basically. So it'll be 1, 2, 3, 4, 5. So each 1, 2, 3, 4, 5 is a power of 2. So it'd be 2 to the power of 0, well, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So 2, 4, 8, 16, like that. And the reason for that is that I want to, if you just increase it linearly, it doesn't really give you very much effect, right? The noisiness takes over. You want to increase these values by large amounts, but I don't want to increase them by such large amounts that I'm suddenly running a really long code that goes on for ages. So I'm using powers of 2, and it's a sort of nicer way of just getting a little bit of an idea of how the smaller scale of the system evolves as you increase the number of loops on each individual inertial reference frame. So this is what we see with just 1 time step. You can see there's a definite decrease of the standard deviation of the distribution at this stage, and this is and if we look at the mean, I mean, this is obviously the distribution here is around 1. You can see the distribution tends to be around 1. This is the average scale of the system, the average speed of the system. It's definitely staying around 1. And if we look at the average value is very close to 1 here. And of course, that's just for 1 time step, so it's not going to be very interesting. We want further time steps, so we do 2 time steps. We get something like this. So again, standard deviation is decreasing. By the way, there's 2 things here. One, the blue line is the standard deviation of the mean. The yellow line is the standard deviation of the median. As I said, because there's a large skew in this data of the scale of the range of the wavefront speeds, it makes a lot of sense to look at the median and the mean as well. And now here it's gone up a little bit, but I think that if you look at even more loops, still it continues to go down. I think if we were to continue this with more loops, it would actually eventually go down again. But this is an area of further research. You know, this is something that we want to be looking into in more detail. Obviously, we're increasing the loops by like powers of 2, but maybe we can increase it by powers of 3. Have done some simulations like that. What happens if you take it to 10,000 loops or 1,000,000 loops or 1,000,000,000 loops? You know, obviously that's not necessarily feasible, but you know, at least at smaller scales, you have a smaller number of possible states that the system could be in. This is why I'm really interested to try and get the system working within the Wolfram model framework, because that will be a way of exhausting all possible paths. Now that might be very computationally intensive, but by exhausting all possible paths, we'll avoid any errors that there might be as a result of statistical repeats, or there not being enough of we're not measuring enough of the states, but we're able to get a sort of overall idea. Anyway, if you keep looking at a lot of this data, you can see that the values very much tend to be around 1, and the thing that's really striking is that even at really large scales, I mean, this is a very small scale, we're looking at sort of 4 time steps here we're looking at 5 time steps, and this is the standard deviation again going down, and here's also the distribution again, it's around 1. No matter what the scale of the system is, it still is around 1. Like if we go back to here again, if we go back to here, we look at the scale of the system again, it's just 1. It's around 1. It stays around 1. This stays around 1 as well. And the mean again, is skewed, but then again the data is largely skewed, so that doesn't necessarily mean that you're more likely to see a value around this value. There's something holding it to this value. So then the other thing I wanted to do is I wanted to actually investigate and look at the actual distributions. So I did that for m is equal to 5. We're keeping m is equal to 5. 3 time steps, and we're looking at basically initiating an inertial frame after 3 time steps in the second phase. Right. So you imagine there's like 2 phases. There's phase 1, phase 2. We could call this phase 1. Phase 1, and this is phase 2, right? Okay, and wait, where was I? I've lost myself now. Is it here? No. Here? Yeah, here we go. Okay, so the first one we look at just doing 1 loop for each inertial frame, right? And so we get a very sort of it's something that looks a bit like a Poisson distribution. I'm not particularly surprised about that because it's we're going between 0 and infinity essentially as the possible values, and we've got a mean around a certain value, and this is the mean, right? This is the mean that was calculated for this particular system. This is the mean of all the inertial frames speeds. It's about 1, isn't it? I mean, of course, we're only looking at 3 time steps. We need to look at further time steps and investigate further. But like I said, we did 500 time steps here, and we got, quite low down. I mean, obviously, it's not exactly 1, but the mean is it's around 1. The middle point between the median and the mean is constrained to be around 1. So I don't believe that there's going to be a massive effect of increasing the scale of the system when we increase the time scale of the system. So just to finish off, here's the distribution after for 1 loop, and there's the mean. You see the mean is right on 1. And then if we do it again, this is the distribution for 10 loops, right? We did 10 loops, and you can see it's homing in on 1, and we do it again, and even more so. And these values here, by the way, just so you can see these values here, this is the standard deviation of that. So 0.60, and then here, this is the standard deviation again, and there's the mean. That's the mean value, and then here's the standard deviation again. So I want to look into this in more detail. So there'll probably be a 3rd part to this as well once I've got some more data on this. But essentially what I'm trying to show is that no matter what your state is, if you loop over enough loops, if you take a large enough sample of a given state and evolve it, you end up with a velocity or a sort of effective velocity, observed velocity, that sort of is constrained to be around 1, irrespective of what the scale of the system is, and that's the velocity of a light pulse between two points in space in an inertial reference frame. Okay, so I think that's it. Yeah, if you have any questions, do get in touch, and I hope to be meeting some people from the Wolfram Physics Project, hopefully at the summer school this summer, if they want to talk to me. But anyway, I'm going to continue on with this research, and if I get anything that's even more concrete or even more compelling, then I will continue to make more videos. Okay, thank you very much for listening.